So welcome guys. Please subscribe to my channel. So in this video, let's prove this Banach fixed point theorem. Okay, I think this theorem is famous. I mean, if you see the Apostle Ruding's textbook in advanced analysis, or basically the introduction to analysis. Okay, so let's talk about the idea and quickly introduce the notation. So let XD be a complete metric space, right? So basically you have a distance called D. Okay, so but I'm a little bit lazy, so I like to use absolute value. But you can view this D is not actual absolute value, is a abstract metric space. So if you run X equal to contraction mapping, if there's a Q, right, which that if you start from X, Y, and you map to Tx and Ty, and their distance will be lesser or equal to dxy by some by some number which is greater than 0 but less than 1 for all x, y, and x. Okay, so the theorem says that if you have non-empty complete metric space and you have the contraction map, then you will have a fixed point. Okay, so that means you can find the x star such that tx star equals x star. Okay, and there is an algorithm to find x star, right? You just start from any point. You just pick arbitrary x0, and then you take tx1 to be tx0, x2 to be tx1, and you keep going, and finally you will prove that the xn will approach to s star. Okay, so let's prove. Okay, so the idea is that we want to show that x0, tx0, ttx0, tdtx0, keep doing. Then this sequence is a Cauchy sequence, right? And we know that this is a complete metric space. So by definition, a complete metric space means that every Cauchy sequence converges. Okay, so that means that we want to prove that when n greater or equal to m, then if m is greater than some positive integer, if we can bound this xn by xm by arbitrary small epsilon, then we will prove that it's Cauchy sequence. Okay, so this proof is very easy. Let's just go to the detail. Okay, so we need to bound this xn minus xm, right? But this looks difficult. So how about we bound the xn plus 1 minus xn, right? So xn plus 1 minus xn by definition can be proved to be q to the n x1 minus x0, right? Just using a definition n times. So original xn minus xn can be written as xn minus 1 plus xn minus 1 minus xn 2 and 2 and 3 up to m plus 1 minus xn, right? So just using the triangular inequality, right? So this guy is q to n x1 minus x0, and this guy is q to n minus 1 x1 minus x0, and this guy is q to m x1 minus x0. Okay, so summary, I get qm plus 1 up to qn. Okay, so I can pull out qm, and the rest will be 1 plus q up to qn minus m, right? But I can assume, because n is so to bound it, right, I can assume n to be infinity, so it will be just the geometrical series. So this guy can be less or equal to x1 minus x0 q to the n 1 minus q. Okay, so that means for epsilon greater than 0, I can choose m to be large enough, right? Then the q to n can be arbitrarily small. So xn minus xn can be arbitrarily small. So by completeness, xn will converge because this guy is a Cauchy sequence. Okay. Okay, and obviously that by definition, right, your contraction, your results will be give you a fixed point tx equals to x, because when n goes to infinity, this sequence converge. Okay, so finally, we want to prove a small results that actually we have a unique fixed point theorem. Okay, so finally we already have a fixed point, right? So let's prove that the fixed point is unique. So let's assume that, well, we have two fixed points, right? Base x different from y, such that t as x equals x and ty equals to y. But t of x minus t of y will less or equal to q x minus y, right? But x minus y will less than or equal to q x minus y. But q is from 0 to 1, so x minus y will be 0. That means that the x must be equal to y. So that means the fixed point must be unique. Okay, so this is a very easy theorem. I think it's very elementary. Okay, I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.